Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Simone Casassus with us today. Hey, Simone, how are you?
Good here. Nice to meet you, Francis.
Nice to meet you, Simone. Simone, where are you located at?
I'm in Chile.
Cool.
On the coast in a place called Puertecillo. By the seaside. So
very nice. Very nice.
It's a warm and sunny day today.
Even though it's winter, it's
well, it's winter, but it's very sunny outside. And
nice. Nice. Oh, beautiful. Oh, that is lovely. Oh, thank you for sharing that. Now I'm all jealous. You have an ocean. So I'm in Phoenix here, and it's summer, and we are getting our rainstorms, but we don't have that beautiful blue ocean that you just showed us there in the Pacific. So I'm going to have to come visit you, and you'll have to take me to the beach.
Oh, yeah, definitely. It's a very cold sea, I must say. Rough and cold sea, but
cool. And I think you also win the prize for being the first person coming in on satellite internet. So we'll see how this goes on the band.
Okay, we'll see how it goes.
We'll see how it goes. Be very good. And Simone, what do you like to do for research?
So since 2010, I've been working mostly on planet formation. So cool. During my career, I've switched from different fields, but what I've been working most on recently is the observational planet formation. So trying to understand the workings of protoplanetary disks.
Cool.
Mostly.
Cool. Very nice. And that is going to bring us to this very lovely. This is an APJ letter. It's open access, people. You can go get it for free. Go grab a copy. The Doppler flip in HD 100/546 as a disk eruption, the elephant in the room of kinematic protoplanetary searches. And Simone, take us away.
Yes, so thanks, Frank. So this is my latest paper on protoplanetary disk kinematics. And this is work done in collaboration with, these four co-authors. Miguel Cárcamo was crucial to the synthesis imaging part. Synthesis imaging is this technique by which you turn interferometer data into images. Antonio is the ALMA expert on board, so expert on all those details about the pipeline and calibration and so on with ALMA. Cool. Philip Weber is a theoretician, is a hydrodynamicist who helped with one of the interpretations for the phenomenon we observe. And Bill formulated a very interesting idea. He's also an observer, protoplanetary disk observer, and he had the original idea about one of the two interpretations in the article.
Cool.
Yeah. So here in this letter, we report on very detailed ALMA observations, so long baseline, fine angular resolution ALMA observations of a prototypical Herbig AB star, which is called HD 100/546. So it's a fairly massive star on two solar masses, fairly massive compared to typical protoplanetary disk masses. Plus two young stellar object, which has essentially dissipated most of its envelope, and it still contains lots of gas in its disks, so that giant planet formation is thought to be ongoing in the system.
Nice.
That's right. So in this article, mainly we followed up on a previous project, also based on ALMA data, but not in such fine details. And then the idea was to try and see if we could learn more about the phenomenon we found. So the point is that you know that when planets form, they disturb their parent disk, right? So they carve away a gap usually. It was thought in the beginning, in the early 2000s, you know, that was enough to identify a newly born protoplanet. And the problem is that there's many ways to form a gap. It's not only planets that carve away gaps, you know, there's many other physical processes. And so at the Universidad de Chile, we started a line of research in 2015 to try and identify protoplanets based on their on the kinematics of the host disk. So it's a bit like when you detect an exoplanet, you know, where the first time you detect first detection of an exoplanet was with the Doppler recall of the host star, right? So this is kind of a similar idea. Try to pick up the protoplanet by the velocity perturbations in the host disk. So the disk is perturbed, the velocity field is perturbed in the vicinity of the protoplanet.
Yes. And
even in the vicinity of the planet itself, you expect to have a circumplanetary disk that's spinning fast. And you should see this as a broad line in molecular traces. Yeah.
Yes.
The idea is to pick up such planet with the kinematics. And here in this system, we found a huge velocity perturbation. So maybe we can scroll down to figure 1 to illustrate the gap. There is the gap in this system. So this is a very well-studied disk, and which has this central cavity in which people have thought to, people think to have identified a giant planet. I mean, the Sean Britton et al. Have identified a probable circumplanetary disk inside the central cavity here. And you can tell that the ring we see in the Alma continuum in figure 1A is modulated by complex structure, you know, which is very dynamically active. You can, just by the looks of it, you can tell that things are going on and being perturbed by some massive body embedded in the system. And so this letter is more to do with the gas, actually. But it's important to have a look at so figure 1B is just the same as figure 1A, but this is more like the standard way to convey interferometric images in the radio interferometric community. Now, it's good to linger a little bit on figure 1 to advertise our imaging package, which is called UVMEM. UVMEM delivers this model image, which we see on the left, and its restored version, including the visibility residuals, is on the right. That's right, which is what would be comparable to standard imaging packages such as CLEAN. So with this, we also image the CO2-1 line, which is a rotational line of carbon monoxide. And I think the best way to see this would be in figure. I think I've lost the paper here. Let me see if I can find it easily. Yes, that's right. That's right. So maybe figure 4.
Figure 4.
Yeah, figure 4, I think.
Kinematic maps, non-axial.
So in figure 4, so that would be, yeah, these are the usual movement maps. This is figure 4. I finally see it. So that's the delay with the satellite connection.
That's the delay we have.
Yeah. So the on the top left, we have the velocity centroid. And the contours outline the continuum. And you can tell that in this velocity centroid map, so this is like the average velocity in each line of sight, you know, we have a typical Keplerian rotation pattern, you know, like disk is spinning and it's rotating anti-clockwise, so that the red lobe is receding from us and the blue lobe is approaching us.
Nice.
And you can tell that near systemic velocity, so the white stuff, the velocity field is perturbed. You can tell that there's like a wiggle. I mean, it doesn't look smooth. Yeah. So, yeah, so it doesn't look quite look smooth, and there's a readily visible velocity perturbation, and the main result of this, the main how could I say, the main added value from our analysis is having subtracted this the uniform background. So you see that the disk essentially is a disk, which is essentially axially symmetric, but not quite. There's some local perturbations, okay? And so we subtract away the axially symmetric background, okay? And we do this by extracting a rotation curve for the disk, the same as in galaxies. So we can estimate the rotation curves, which would be like the radial profile for the tangential component of the velocity field, you know? And if you do that, you get figure 4C. So this is the observed velocity field minus this model velocity centroid, which is the axially symmetric one, okay? So these are the non-axially symmetric velocity components, okay?
I'm with you, yep.
And we can also do this with another version of the rotation curve shown in figure 4B, because in which we don't require the velocity field to be perfectly axially symmetric. It is axially symmetric, but not quite tangential. You could have, because you can imagine like a velocity field which is three-dimensional, meaning like the rotation curve is tangential, but you could also have a radial or a vertical velocity component, which is also actually symmetric. And so this is what we call the meridional rotation curve. So with meridional flows, okay? These two flavors of the rotation curve. One is purely tangential and the other one is tridimensional. Both are actually symmetric.
Yep.
And what we have on figure 4D is the crux of the matter. When we have that, we see that the velocity perturbations are bang on the dust continuum emission. So what we see in the ALMA continuum is the dust, and we see that the largest velocity perturbations align very well with the dust continuum.
Yeah.
Now we already knew that, but we knew that the velocity perturbation aligned with the continuum, but we didn't know its distribution exactly. And so with the tools we have, we can try and imagine how this looks face on. So I'm trying to deproject everything and have a look at it face on. So it's not so easy because the disk is thick and its flare and CU comes from higher up than the continuum, which comes from the midplane. So there's a bit of a hurdle there, but we can overcome this and show figure 7. Figure 7, then we see a face-on deprojection of these velocity perturbations.
Very nice.
And how they align with the continuum features.
Okay. So we'll do
exactly figure 7. So
we just got bandwidth. We'll wait.
So the figure 7B mostly is the main result of the paper.
Okay.
So in this figure, we've filtered the continuum to highlight structures. This is a high pass filter.
Yes.
We see that the velocity perturbation really nicely align with the structure in the continuum, right? They're bang on top of this continuum ridge. We also see that the blue side curves along what would be the disk minor axis, because in this, the orientation of this face-on deprojection is such that the disk major axis is upwards. So, which was north, you know, but so that would be the disk major axis. This minor axis is sideways. And that, I mean, if we see a strong velocity perturbation along the disk minor axis, it means it cannot be tangential because of the velocity tangential component doesn't have any line of sight projection along the disk minor axis. That's the way it is.
Right.
That's how the geometry works. And so if we see signal along this y equals 0 in this plot, so sideways, it means that the velocity perturbation is not tangential. It's either radial or vertical, okay? Yeah. And so that is very intriguing, it's very puzzling, kind of disappointing, because the whole point here was to try and pick up protoplanets, but something massive enough to perturb the local Keplerian velocity field by 30% or so, which is what we see here, needs to be pretty massive, you know, like 10 Jupiter masses or so, and should carve away a gap. So why are these velocity perturbations inside the ring and not inside the gap? You know? Right. So that is the elephant in the room. This is probably the system with the largest velocity perturbations we know of, you know? Okay. So this is where we see the largest velocity perturbations, so the largest non-Keplerian velocity components in any protoplanetary disk. And they don't make sense in terms of an embedded protoplanet, because the embedded protoplanet would have to be very massive and should clear away a gap. You know, so maybe what we're seeing is a giant in the process of clearing the gap, and that would be a very, very peculiar strike of luck, because such a process would last maybe a few thousand years, 100,000 years, and the lifetime of the protoplanetary disk is 10 million years. So it's kind of difficult. It's kind of difficult to believe that we're catching the system right in the act of evacuating the gap. That's quite unlikely. And you know, we've been scratching our head with this phenomenon, not knowing what it means, because another thing is the continuum is optically thick. So we can't see behind it. So we're only seeing the side of the disk that's facing towards us. Yep. And so the disk, the top side of the disk. And the back we don't know about, because the continuum is optically thick, so we can't look through. Yep. Yeah. And so it also means that the ridge we see here might not be a density structure. It might actually be a temperature structure. Yeah. So meaning hotter stuff. And other workers have studied the system, and right where we have the blue side of the Doppler flip, we call this a Doppler flip because of the shift between red and blue. And other workers have detected traces of shock tracers in the blue lobe. SO, I think it did, sulfur oxide maybe, SO. But that's a sulfur a shock indicator. I'm not a specialist in astrochemistry, but I know that this means that sulfur mantles being evaporated away from grains in shocks, so in high temperature regions, much like what could look like a temperature hotspot and what we see as a continuum ridge, you know. So the idea came up among this collaboration that perhaps this Doppler flip is due to an embedded outflow. In the same way that when stars are formed, we have angular momentum dissipation through outflows. You know, giant planets have the same problem, or even anything accreting must dissipate somehow angular momentum. Yeah.
Fair enough, sure.
And so it's not a crazy idea to extrapolate the young stellar object outflows to the planetary mass regime, you know? And so we figure, what if this is a super Earth, a 10 Earth mass object, not massive enough to evacuate a gap, but that launches a wind. So the wind is collimated, embedded deep in the midplane, but it catches momentum, and as it reaches the surface of the disk, it's easier to perturb the velocity field, because there the density is lower, and so the momentum carried by the wind of the protoplanet can more easily perturb the ambient velocity field, you know. And so that's the idea, that we have an embedded protoplanet launching a wind and depositing momentum in the surface of the system. We have no way to prove this.
Sure.
Pure speculation. but it's all that makes sense. So you can go down to the interpretation and consider two different avenues.
Okay.
So the first one is that which I have just described now, which is this disk eruption. So, and call this a disk eruption because it's a perturbation on the surface of the disk. It stems from deep within, something inside the disk in the midplane, most likely, is launching this wind that we see as a perturbation on the surface. So that's why I call it a disk eruption.
Yep.
So if we scroll a bit downwards, a bit more, we have one of the, I think an equation that can describe the phenomenon is equation 5.
Equation 5. M dot.
That's right. So we have this shell velocity. This is the mass loss rate of the outflow, the M dot S, if you want. So this is the mass loss rate of the embedded protoplanet. That's traveling at velocity Vs, you know. And so if the velocity is constant, what we have on the left is a variation of momentum, and it balances with the run pressure. The ambient pressure in the in the surrounding medium.
Right.
So that would be the pressure that's containing the embedded outflow. Just to have an idea, because we don't see the outflow puncturing this. I mean, if we had a very strong outflow that would strong enough to puncture the disk, we should be able to see like a huge lobe coming towards us and a huge lobe receding from us on the back of the backside of the disk. Even though the disk is optically thick, if you recede far away from the disk, then you have a clear line of sight. So we know that the outflow is not puncturing the disk. It's being contained by the disk, you know. And so that's why I balance the run pressure of the outflow with the ambient pressure. So that's a typical argument in the ISM used by supernova remnant workers to estimate radius of supernovas. But we can use this argument to work out what sort of mass loss rate we would need to explain the phenomena. And it turns out that we need to create a 1 to 10 Earth mass object in about 1 to 10 million years, which makes sense, which is sort of in the ballpark of what we expect from planet formation. So we have no way to prove that this is indeed an embedded wind, you know, from a protoplanet, but it's not outrageous. It's not outrageous to say so. It doesn't violate any laws of physics, and it's consistent with the observations.
That's good.
So, so that there is another interpretation, which was that maybe the disk was undergoing late accretion, like meaning stuff wasn't falling on the disk, but we kind of ruled it out, really. So I don't know if it's worth expanding much on it. So I think that the only viable interpretation we could think of is this one. Some people could think maybe there is an embedded maybe the inside the cavity we have a star. Maybe this is thought to be a single star, but maybe it's actually a binary. You know? But we performed very deep SAM observations with the VLT in the optical infrared. These are interferometric observations in the optical to pick up companions inside the cavity, and we could rule out a brown dwarf. So it's not a stellar companion, and in any case, anything inside the cavity should generate the largest velocity perturbation in its vicinity, not far away inside the ring. So that is the point about observations. I mean, we confirmed our previous finding for a big velocity perturbation aligned with the ring. It was very puzzling. We didn't know what that meant. And with this new observations, we could tell We could pick up more structure within the velocity perturbation, see that it aligns very nicely with the continuum ring, probably associated with hot regions. So maybe shock regions, maybe this is where the outflow from the protoplanet is hitting the disk, and that's why we have a shock. Yep. And so the main message is beware of interpreting protoplanetary disk kinematics only with the gravitational interaction of a protoplanet. So this is the elephant in the room, right? Because we can't explain, if we can't explain this phenomenon, there's no point in trying to understand those tiny velocity perturbations elsewhere. You know, you need to understand like this most obvious ones first. That's what I mean.
Very cool. Very cool. Simone, thank you so much for walking us through this very lovely APJ letter. Thank you. And you mentioned it a couple of times. And so I'll ask a little bit, sort of, you know, where do we go from here, given this article? Are there additional ALMA observations planned for this object, or are there other elephants in the room to go ahead and take a look at ALMA, or with other wavelengths? Could there be some hydrodynamic simulations of the scenarios that were mentioned to see if it pans out hydrodynamically? And just kind of, where do we go over the next 2, 3 years, 5 years on this topic?
Thanks for the question, Frank. I think there's lots to do, and the community is very interested in the kinematics of planet formation, trying to pick up the planets this way. There's many programs, very many programs going on, even an ALMA large program led by other people. But what I can say for now is that in every single instance where we see velocity perturbations, we see that it comes from the surface. So the surface is showing the perturbation, and tracers that go deeper, molecular tracers that sample the kinematics deeper within the disk, do not show any velocity perturbation. So that doesn't sound quite like what we expect from the gravitational interaction of an embedded massive body, and is more consistent with what I'm proposing here. That maybe we have embedded planets, but the impact of their outflows is modulating the disk kinematics. Is what we see. So I think that the most important part of the work to be done at the moment is theoretical. We need hydrodynamical simulations of such winds. Actually, it's very surprising. There's very few hydro simulations of winds from planets. So only a couple of papers. So we observe winds in the hydro simulations only when the magnetic field is included. So from the papers I've read, you get winds from the protoplanet only when you have a magnetic field, so very much like the stars. And the lower mass range, like super Earth mass range, has not been modeled yet. So it's not easy, I suppose, to model, you know, all scales from a few Earth radii where your wind is launched all the way to
the disk,
200 astronomical units.
Exactly.
So it's
a lot of resolution.
Yeah, so I guess there's a problem there. So
I'm
not an expert. I've teamed up with theoreticians to look at this issue, but I think that the most important part of the work is theoretical, actually, because we already have lots of observations that are quite puzzling. We can't understand them really. So
cool. Very nice. Well, I really look forward to seeing some progress in this over the next couple of years, and we can say what the elephant is. That would be very nice.
I hope so.
Very cool.
Maybe it's just a mouse.
Yeah, could be. Well, that's a good cover. A mouse is an elephant. Excellent. Super. Awesome. Simone, thank you so much once again for walking us through your very lovely article. And that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.